Yeah, so who am I? Just to start, I work for Cloudera. I'm on the Lucene PMC, and I'm an Apache member. I started playing around with Lucene in 2006, been a committer since 2008, Solr committer since 2009. So I've been doing this for a little while now. This is actually me riding the mechanical bull, which when we released like Lucene 4.2, I think, that night, I was at a bar with Robert Muir, and he made me ride this bull and took some pictures. So that was fun. Also, I keep hearing about cats. I love my dog, and this is my dog. Very good-looking dog. So yeah, I'm talking about Solr and kind of NoSQL and SolrCloud, and I'm just gonna, talk about kind of how they overlap and guess where I think things are going. To start off, I'm gonna talk about big data because it's a nice buzzword. Everyone's interested in big data. Big data is getting bigger all the time. Total, I looked up some numbers. The most recent stuff I could find that seems somewhat reliable says the big data market reached 11.4 billion in 2012. I loosely heard a while back that like the enterprise software market is something like 100 billion. So already being at 11.4 billion, I guess, is why all these Hadoop companies and NoSQL companies are raising like $80 million, $100 million rounds. People are pretty interested in this stuff, especially VCs. Big data market's projected to reach 18.1 billion in 2013 for an annual growth rate of 61%. So yeah, big data is getting bigger. These guys that I found these numbers, which I should attribute, but I didn't, it says it's on pace to exceed 47 billion by 2017. A lot of money in this stuff. So when you're talking about big data, you're talking about basically scaling from one machine to many machines, and you kind of have the same issues that you have with one machine. You got to deal with storage, you got to deal with processing, and generally you end up having to deal with search. According to that report that gathered those numbers, there's two standouts in the big data market at the moment, Hadoop and NoSQL, basically in terms of which ones are generating revenue. Search doesn't quite seem to be there, but it actually seems to end up playing a big role both in the Hadoop world and in the NoSQL world. Yeah, finally I attribute these guys. Wikibon is who put out this report that I was reading. So they kind of end their whole report on big data with ultimately the NoSQL market is largely up for grabs. Each NoSQL database has its related strengths and weaknesses, and no one SQL database currently does it all. Big data practitioners must take a number of factors into consideration when selecting a NoSQL database to facilitate large-scale transactional workloads, including scalability, performance, security, and ease of development. So basically they're saying the big data marketplace is still kind of up for grabs. There's a lot of NoSQL solutions at the moment, like Hadoop. It's making a lot of noise, bringing a lot of money. So initially, I'm going to talk just a little bit about history, relational databases. This was kind of before the NoSQL movement, the classic way to store your data since the 60s or 70s. This is how we've been doing it. You get ACID, you get transactions, you get SQL. Everybody loves and knows SQL. I know at my first interview at the first job I had, the first thing was that they asked me was, can you write an SQL statement on the chalkboard or whatever? I declined because it seemed like a dumb question, but I didn't get that job. So yeah, scaling relational databases ends up being a little bit hard. There's a lot of strategies that you can use. You can kind of shard things. You can, kind of take things that aren't related to each other and put them into other databases. Overall, it ends up being kind of hard, and you really usually have to get rid of most of the things you want to use a relational database for, like joins and some of the ACID properties. So it's hard. It is possible. Facebook has like a humongous MySQL cluster that's probably as big or bigger than any NoSQL cluster. So it's not impossible, but basically it's not so simple either. And then also there's the old impedance mismatch between basically writing data structures in Java or whatever, and then having to transform them into something that that a relational database understands. This is why we got things like Hibernate. 5 years ago, I was really into Hibernate. At the end of the day, what I figured was it just took a complicated situation and pushed it to a new complicated situation. And honestly, really, what I was usually doing when I first started needing to store data was like, I just had some data and I needed to persist it. And the main reason I would use a relational database is because you want durability, you want to be able to access the database concurrently. You want a lot of the properties that relational databases give you, but I mean, honestly, I wasn't hardly ever doing joins. Sometimes you have to do joins and add, you can add basically triggers and all of these things that I learned in college, but generally didn't have to use. A lot of the time, I'm just trying to store some freaking data. And having to go through a relational database and deal with Hibernate and all these things just to store some data kind of sucks. And I actually, at one point, was really into these object persistence libraries that you could basically just give a Java object and it would persist it for you, but kind of better than you'd do yourself with durability and all of these things. Although a lot of those at the time didn't scale beyond one node. So yeah, relational databases, they're awesome. They're not going anywhere anytime soon, but scaling them is kind of a pain. So yeah, a little history on Search. So Search for a long time was really expensive. Even when I started doing Search in like 2005, the company I worked for used Fast. They had like some 800 billion documents, and they paid hundreds of thousands of dollars in licensing fees. They had like a team of 20 people come in to set up their Fast installation. It was a big, nasty, complicated mess. I remember the first time I was introduced to the documentation, and it was like printed out in these books, maybe like 20 books stacked on top of each other on this desk. So a little crazy, little expensive has been kind of the history of Search. Luckily, Lucene has kind of largely changed that by coming out and being better than most other search engines these days, much faster, more features. Search, like most things, is kind of moving to the open source world, which is pretty nice. But yeah, in general, once you get a lot of data, you kind of want to be able to search it, right? I mean, it just makes sense. You want to find stuff in your data, and search is often the way to do it. So yeah, enterprise search, very interesting thing has been happening over the past 5 years. There's been a lot of consolidation. There used to be all of these independent enterprise search companies. This is just like a sub-list. Verity, they were acquired by Autonomy, some consolidation there. Fast, acquired by Microsoft in 2008. The company I was working for knew they were switching search engines right then because they used Linux, and well, Microsoft at the time said that, don't worry, Linux support isn't going anywhere. Of course, a couple years later, there goes Linux support. Endeca, acquired by Oracle in 2011. Autonomy, acquired by HP in 2011. Vivissimo, acquired by IBM. Everyone has basically been bought out, which has been great for open source because most people don't like when the company they're working with is bought out and then everything changes. And vendor lock-in kind of sucks. And that's been a big boon for Solr. So, a little bit about NoSQL. Kind of an interesting term that's kind of hard to pin down. I guess it was coined in like 2009. I don't remember the guy's name, and I obviously didn't put it down here, but they were having some meetup about these new database solutions that were coming up, and they were looking for like a Twitter hashtag that was kind of short and that they could use to kind of promote this meetup and these new technologies. And I believe I read that in the Cassandra IRC channel, somebody threw out, let's use NoSQL, and that's kind of somehow stuck since then. Doesn't make a lot of sense. Some people think it means, not SQL, no SQL, which isn't really what it means. It's supposed to mean not only SQL. Some people make the argument, though, that second O should be capitalized if it's not only SQL. And then they're also like, well, if it's not only SQL, that's not very helpful because that includes SQL. And obviously, when you're talking about NoSQL, you're not generally talking about relational databases. So the recommendation I've seen is to forget about what it means and just, it's an acronym. And it basically means, I stole this from NoSQL Distilled. When NoSQL is applied to a database, it refers to an ill-defined set of mostly open-source databases, mostly developed in the early 21st century, and mostly not using SQL. So, roughly, there you go. There's a variety of kinds of NoSQL databases. These are pretty much the main ones. You've got your basic key-value store, your classic kind of distributed map, basically hash map type structure. Columnar, can't explain that. Other people say column family. That's what I should have wrote. Document-based and graph-based. So I'll talk a little bit about each one. So NoSQL, because it's so loosely defined, it's very easy to say, actually, it's existed for a long time. Yeah, most systems can kind of fit the NoSQL definition. Some of the more popular ones that kind of fit a long time ago, BerkeleyDB, Wikipedia. The Wikipedia article claims that it's like the most widely used database in existence. I didn't really look at the citation to know if I believe that or not, but it's been around since like 91. It's hard to say necessarily when it was started, but that's the best I could find. Oracle owns it now, previously run by Sleepy Cat. The CEO of Cloudera actually ran that company, so I have some connection now. Lotus Notes was an early kind of NoSQL implementation. And then this one called Bayou, which I can't remember if it was Yale or Stanford that came out of, but that was in '96. There's a paper about that, and that's kind of an early NoSQL guy. But in the modern era, what really kind of started off the big 2009 NoSQL movement was a couple papers published by a couple well-known companies. Google did the Big Table paper, and Amazon did the Dynamo paper. Basically, two huge companies that have tons and tons of customers, tons of data. They needed to solve this problem that relational databases are really hard to scale. And they kind of both had different problems. Big Table kind of originated in needing to basically store hyperlinks and attributes of those hyperlinks for the entire World Wide Web, which means a whole hell of a lot of hyperlinks. And Amazon needed the millions and millions of people who shop at Amazon to be able to work with their shopping cart and save things all the time. Basically, they calculated that anytime you tried to add something to your shopping cart and for some reason it failed, you need to do a write to add that to your shopping cart. That cost them a lot of money, and so they built this system to be very, very highly available for writes. So they're kind of solving two different problems, have two different architectures. They publish these papers, and open source guys love to take papers from these companies and turn them into projects, and that's kind of what's happened. So each one kind of has derivatives, NoSQL derivatives that kind of follow their architecture. Just to mention a few, Dynamo has Cassandra, CouchDB, Voldemort, Riak. They have somewhat similar architectures. Big Table, also Cassandra, which is interesting. I'll talk more about later. HBase, Redis, Hypertable, Accumulo. Also, they've got kind of software each has a software as a service that's loosely based on those original designs. I don't know if you've ever used Google App Engine. I love it because I love GWT, and it's really easy to go to Eclipse, say start new project, have a GWT project basically pre-made for you, plug in a bunch of stuff, deploy it. Simple access to big table-like stuff. Really, really cool, I think, although you get a little bit of vendor lock-in on that. But I love making projects for App Engine. And then Amazon has DynamoDB, which I don't think actually uses Dynamo to my knowledge, but it's based on the same principles. So basically, though, when it comes, like my original NoSQL definition said, when it comes to NoSQL, open source is pretty much where it's at. Almost all of the popular NoSQL engines are open source engines, which is kind of interesting. And it basically just seems like the software world in general is moving towards this, which we'll talk about perhaps why in a little bit. So pretty much I'm not going to be talking much about anything that's not open source, which I like. I'm a big open source guy. Moving on. So here's an interesting survey. I actually tweeted a link to this a little while back. Black Duck Software and Northbridge put out this survey for the last few years of basically, why are people using open source? What are the reasons they're into it? And it's interesting. The last few years, the top reason has been freedom from vendor lock-in. And probably that's a backlash against all of this consolidation and the fact that all of these large companies bought these enterprise search platforms and basically changed them or put them into other products so that people that were using them couldn't use them the same way. And so they're basically looking for an escape from this vendor lock-in. The other reason is lower acquisition and maintenance costs, which in the end could be argued. Licensing costs for search were definitely very high, but when you go open source, you definitely, software is free, but you pretty much still need some sort of support contract, and you still have, a lot of costs. So I don't know if it always ends up being that much cheaper, but it's definitely usually somewhat cheaper. So basically, in 2011, better quality software, which is the reason I've always thought open source was the best, was the number 5 reason people used open source. In 2012, that moved to number 3. And what's really interesting is in 2013, finally better quality software is number 1. And that's where I think it should have been all along. This is why people should use open source. When you work for a company and you're making software, like, stuff is done because of deadlines. Stuff is done because some boss who doesn't get it said this is how it's going to be done. And basically, over time, this type of stuff is what creates the huge, bloated, crappy proprietary software that most people who used enterprise search 5 or 10 years ago were used to. This is the reason I have to download 11 gigabytes to run like the Oracle database, because stuff just gets piled in, and it's more about features and selling than it is about quality. The interesting thing with open source is, it's not a rule. There's definitely some crappy open source projects. But for most of the good projects, a lot of the people that are working on the project are passionate about the project. They're not working on it necessarily just because someone pays them. They're happy that someone pays them to work on the project. But most of the guys working on Lucene, they're hacking on this stuff Saturday night, Friday night, whenever they want. They care about the code. And in the end, that creates better software, I think, because things aren't about deadlines, things aren't about features. If I want to ram something in because Cloudera, or when I was at LucidWorks said, we need this in there, get it in, and somebody else like Robert thinks that's a bad idea, he can pretty easily stop me and say, look, this isn't very well thought out, you're just doing this because somebody wants it. And so he can stop me because he's interested in quality code. And in most, not every, but in most enterprise situations or commercial situations, that's not the case. And so I think better quality software is just a huge reason to use open source. Over the long term, open source guys are really looking to maintain their code in a nice way that management can't as easily screw with, because usually multiple companies are involved, and so not any one company can really damage things. Which is why I don't believe as much. There's actually a lot of companies that have open source projects where they're pretty much the sole contributor. They say it's open source, they give the code out there, but all the committers pretty much work for one company. I think that has similar problems. It's not as bad as commercial software, but I think it has similar problems. So that's why I like Apache. I want to kind of compare Solr and SolrCloud and where it is with kind of its NoSQL features with a lot of the NoSQL databases that are out there. But there's a lot of them. There's a ton of NoSQL databases. How do we know which ones to talk about? Which ones are popular? There's a couple ways that I like to do it. One of the main ones, which I kind of stole from Yannick, I didn't really know about Indeed.com before then. Indeed.com is an employment-related meta search engine for job listings. Basically, they take all the job listings they can find and they suck them up. It's pretty much, at this point, the #1 job site worldwide. I think in 2010 it passed Monster.com as the largest job site in the US. It's got over 100 million unique visitors per month. It's available in more than 50 countries. They claim they cover 94% of global GDP. It's just a freaking huge job site. And they've got some awesome thing called job trends, where you can basically put in a search term and get back the percentage of job postings that have that search term. So what better way to figure out what solutions are popular than looking at who is offering jobs with these solutions, right? If I can put in Solr and see what percentage of jobs are for Solr versus another search engine, that tells me a lot about what the popular solution is. Another option you have, which I kind of like, is this German site that I recently found called dbengines.com. These guys basically use a variety of sources to rank search engines, databases, both NoSQL and relational. And so they actually use Indeed job trends, but they also factor in Google Trends, LinkedIn skills, and a variety of other sources. They're not extremely specific on how they do it, so I kind of take it all with a grain of salt. but they basically grab whatever data they can and generate these rankings, which is pretty cool. So between the two things, I think you can get a pretty good idea of what's popular. So as a start, let's put in some common search engines that I know of. I kind of left out Zapier here. I would have put that in, but Solr, Sphinx, and Elasticsearch. So at the moment, Solr is pretty much obviously the most popular one when it comes to job listings. This is the Indeed trends. That works out perfectly because it's the one I'd talk about anyway because that's what I work on. So popular search solutions with DB engines. So this is the DB engines rankings that also takes into account LinkedIn, Google Trends, and other things like that. It lines up pretty much with Indeed, as you might expect. We get a couple other guys in there. Cloud Search, Amazon's new stuff, which is fairly new, so I expect that to kind of rise on the list. I'm a big Amazon fan, so. You've got Compass, which is a Lucene-based solution. Zapier, which I've never looked into too much, the Google search appliance. Elasticsearch, which is another Lucene-based one. Sphinx, which is a C engine that's kind of heavily geared towards working with databases. And Solr. So similar to Indeed at the moment, Solr has fairly decent penetration, which is kind of nice. Now on to some NoSQL databases. So at this point, I just threw in what I've heard of, to kind of see where things shake out. MongoDB, Cassandra, HBase, CouchDB, Redis. These are popular ones that I've kind of come across. Interestingly, 3 of them are Apache. Apache software seems to do pretty good at making inroads in people's minds. At the top is MongoDB. That's been on fire lately. They've raised a lot of money, attracted a lot of developers. It's doing really well. Looks like next is Cassandra, followed pretty closely by HBase. And then you've got Redis, very, very popular solution, I think especially in the Ruby world. And then CouchDB, which kind of a little bit lower than the rest. But it's kind of interesting. You can kind of see, NoSQL kind of started taking the world by storm in 2009. Didn't really start entering the job market until, 2010-ish. And now it's really starting to take off. To get some context of how that measures against other stuff, I threw in, for example, here's Hadoop, which is the top orange line now. So Hadoop kind of dwarfs these NoSQL guys a little bit. Also, they're raising a lot. Cloudera just raised, I don't know, $80 million or something a little while ago. MapR, Hortonworks, the same. They're raising a ton of money. MongoDB and these Hadoop guys really raking it in at the moment from the VCs. And then let's throw in, something else to really get some context of where these guys sit. I put in Java, Whoops, sorry. So, once one of these solutions or Hadoop is as popular as Java, you can expect it to come up here. And then finally, Oracle. Not Oracle database or anything, just Oracle in general, but just to give some context, loosely as popular as Java, which is pretty interesting. So, looks like they're the guy to catch up to. Didn't I already do this one? Yeah, so, well, I'm going to dive in particular and look at the popularity of each different kind of NoSQL database, key value, column family, document, graph. I'm actually going to pretty much ignore graph because everyone else seems to. When you look at the DB engine popularity of graph databases, the top one is Neo4j. Looks like that's the only one to really look into based on popularity at the moment, and it's got a score of about 8. Which when you look at all of the other NoSQL solutions, doesn't really put it on the radar. So I'm not going to talk about graph ones right now, and honestly, I haven't read a lot about them, so I couldn't. In general, I'd like to make the disclaimer that I don't really use these NoSQL databases. I'm pretty much a Solr developer. Before I was a Solr developer, I was a Lucene developer. I love to read about them because I'm doing distributed work, but I don't have to build a solution on them. So I'm not an expert. I'm a guy who's read some about them, and I'm going to tell you some about what I read. There's probably people out here who have built solutions against these things that know a lot more than I do. Just a disclaimer. So let's start with document stores. At the top of the list, like we saw, you've got MongoDB. Its competition is CouchDB, which was, when I was putting in for Indeed job trends, the lowest one. So as far as document stores, Mongo really doesn't have much competition. Below CouchDB, you have Couchbase. That's, I think, the creator of CouchDB kind of went off and started his own commercial thing. He got sick of Apache, and he came up with Couchbase. I think it has like maybe better clustering options and whatnot. RavenDB, which I've heard of, and Monesia, which I haven't. Key value stores. You got Redis at number 1, Memcached, Memcached. I don't really know how they say it, but 2 very popular in-memory key value stores. Then you've got Riak, DynamoDB, BerkeleyDB, SimpleDB. BerkeleyDB for on Wikipedia claiming that it's like the most widely installed database. It's a little surprising that it's kind of low in the rankings, but seems to be the case. Number 10, I'd like to mention Tokyo Cabinet. I love that name. People seem to have heard of it, though it doesn't seem that popular. And then you've got the column-based stores. Top of the list seems to be Cassandra at the moment, HBase. And then you've got Accumulo, which is also, all 3 of the top guys are Apache projects, which is interesting. And then you've got Hypertable, which I see come up now and then, doesn't seem to be so popular at the moment. And now, just as for interest, we've got the full popularity contest. This is from DB Engines. Not only do they rank each of those different types of NoSQL databases and relational databases and search databases, they also put them all together and rank them. And as you'd expect, the top guys are generally the old school relational guys. Oracle is number 1, MySQL nipping at its heels, but these days also basically Oracle. So Microsoft, SQL Server, Postgres, way down there still compared to MySQL. It always surprises me, but it's got a lot of fans, but not the same popularity. Microsoft Access, DB2, all stuff you've heard of. The first kind of surprise, MongoDB at number 7. MongoDB and its popularity does not cease to amaze me. It's pretty crazy. SQLite, Sybase, and this was really surprising to me. Solr hanging in at number 10. Yeah, that's pretty amazing. And then down the list a little bit, Teradata, Cassandra, Redis, Memcached, Informix, HBase, CouchDB. Remember though, this is DB Engines. The way that they do this stuff, you got to take with a grain of salt. They don't explain it well enough for you to be super confident in it. When you look at Indeed job trends, because it mostly matches up with this, I've got some confidence in it though. That's pretty much the list. And in case you forgot, Oracle actually has a NoSQL engine. It's very similar to the architecture of Solr actually and how we did things. But nobody uses it. It seems nobody knows about it. Okay, so that pretty much gave us the list of things that I know that I should talk about in terms of like what engines and architectures I want to talk about. But before I get into that, I want to talk a little bit about CAP theorem because you can't really deal with NoSQL without CAP coming up. The CAP theorem is also known as Brewer's theorem. It states that it's impossible for a distributed computer system to simultaneously provide all 3 of the following guarantees. Consistency, availability, and partition tolerance. So this is similar to like the trade-off between when you're doing software development, features and quality and the time that it takes to do it, right? You can't have all 3. You can make trade-offs kind of between which ones you want. It's not really an all or nothing thing. It's kind of there's a continuum, but you basically just can't have them all. So basically when you talk about the different NoSQL architectures, one of the main things or main reasons you'd choose different solutions is kind of which of the 2 of the 3 that they've chosen, right? And this is kind of a popular way to express this idea that, right, you can't have 2. You either pretty much have a CA system, a CP system, or an AP system. So for NoSQL, things generally boil down to an AP or a CP system. So that's an AP system is basically in the face of partitions, which is, let's say you have a cluster and all the nodes can talk to each other. A partition means, okay, we've cut off the ability for these nodes to talk to each other. A switch went down, a router went down, or whatever, and they can no longer talk. In the face of a partition, do you favor consistency or do you favor availability? Availability meaning if I make a request, does it happen, or how soon does it happen? Versus consistency, if I make a request, is the data going to be kind of stale, or is it going to be strongly consistent? So basically, the relational database is pretty much a CA system. Like, relational databases don't do well with partitions. You can do things like two-phase commit to try to deal with it, but it generally doesn't scale that well, and there's certain situations where you can basically run into like deadlock. That stuff I'm not going to talk a lot about. It's pretty well documented, but basically relational databases don't do well at scaling, which is why we have these NoSQL architectures, which move away from CA systems to choose either pretty much AP or CP. So like Bigtable is a CP system, Dynamo is an AP system. So Dynamo, in the face of partitions, they favor availability. And I believe the Dynamo paper states that's pretty much because when customers cannot write things to their shopping cart, they go away. And also, if your shopping cart doesn't have consistency, it's really easy in the end to like, okay, just show the user the shopping cart that you figured out at the end of the game, and they can notice, oh hey, you didn't merge things right, and they can fix it. So for Amazon, that's a good system, and for like something like Bigtable, those weren't really the requirements that they had, so they chose a different system. And then, of course, there's a continuum between the two different, the AP and the CP system. You don't really have to choose one or the other. Some architectures fall kind of in the middle, and other architectures, depending on knobs you tune, kind of let you choose one or the other. Although, usually they're designed to favor one, and if you tune it to use the other, you're trading off performance or this or that. So like Cassandra is designed so that it can be an AP or a CP system. But if you decide to use it as a CP system, like, I don't know, if you read the Cassandra definitive guidebook, it basically tells you, hey, don't do that. You're going to suffer performance. It wasn't what it was written for, blah, blah, blah. If you listen to the marketing, they're like, hey, yeah, do whatever you want. We offer all these options. But basically, usually, if you want a CP system, you'll pick a system designed for that because it'll generally be more performant and offer more features around that design. So the key design decisions around these different systems, loosely, roughly, I broke it down kind of into three things I want to talk about. The data model, which is pretty much how things are stored and accessed. The distribution model, which I kind of define as like, whether they have replication and sharding and how that stuff works. And then conflict resolution, which is basically if you have multiple nodes and you can talk to the different nodes and you're sending in updates and stuff, how do you make sure that all the different nodes have the same information? Basically, how do you ensure that when updates get distributed around, that the same update on every node wins, so that you have some sort of consistency? And these are basically the problems we were faced with when we decided to make SolrCloud. How are we going to deal with each of these things? Although the data model was pretty much already handled by how Solr does it. So in general, for the data model in NoSQL, you have usually key value stores, which is generally things are stored where you give it a key and that points you to a value. Generally, that value can just be like a binary blob. You don't know what's in it. You can't really introspect it. You just give it the key, you get the value. The other kind is key document. This is basically, okay, you get the key, you get the value, but that value can be structured. And the database might know about that structure, and you might be able to pull back documents based on matching different parts in that structure. Say if it's a JSON document. So it gives you a little more that you can do than just straight key value. And then some of these systems are column-oriented, which basically means instead of putting things on disk in a key value format, you basically lay them out in a column format, which basically lets you read, one of the values for all of these keys for many different records without doing lots of seeks, right? You can just run right down, because on disk you're putting it in the column storage. You're basically to read. If you're reading one column value for 1,000 documents, it's just slurping along the disk. And for like analytics, where you're often doing something like that, that can be really fast. The distributed model, like I said, roughly how is the data distributed across your cluster, sharding, replication, how does all that stuff work? Data versioning and consistency, how is data kept consistent across nodes? You know, basically, how do you roughly get something that's not ACID, but that you don't have random data on all your different nodes, and you can't really count on anything. You got to basically keep some consistency of your data across these nodes. Might be eventual consistency, it might be strong consistency, but that's the other thing. So, the databases we're going to talk about. One of them, MongoDB, since this is obviously the most popular NoSQL solution at the moment. What's its data model? It's basically JSON, although they have a binary JSON format that I guess is more efficient in certain ways in terms of probably being able to compress it, send it across the wire, et cetera. The MongoDB distribution model, they have a sharded master-slave model that they basically call replica sets. And basically how things work are, when you shard, you basically pick a key or a value to hash on, and depending on the hash, you put different data on different nodes, right? So that's a pretty standard way to do things. So the way Mongo does is for each shard, there's a leader, and then you can have replicas, which are basically copies of that data for that shard on other nodes. When you talk to MongoDB and you talk to a shard, you always write to the master. And you generally always search from the master. And this is how they achieve strong consistency. This is how they're a CP system. Because you're only writing and reading from one node, it's really easy to be consistent. There's ways to be eventually consistent because you have these replicas. You can pass a little flag that says reading from replicas is OK. And so replicas asynchronously pull the data from the master, so they can be a little behind. So you pretty much, if you don't need strong consistency, you say, OK, it's OK to read from one of the replicas, and it'll hit those nodes on some reads. And that data might be a little stale, eventually consistent. But you don't have to do that. You can just talk to the master. Data versioning and consistency. So basically, the way that they make sure that things are consistent with the replicas is they basically have a per. It used to be like this global write lock. Now they have like a per table write lock, so that the master basically does this lock to when you add new documents. And because the replication happens asynchronously, they don't really have to worry about any sort of like versioning or consistency. Pretty much how they handle that, which is similar to HBase, is if you want strong consistency, you're talking to one node. You're talking to the master. We do that a little different in SolrCloud. So then, all these NoSQL solutions, like you've got all this data, similar to relational databases. Eventually, everyone wants to be able to search that data. And so pretty much all these NoSQL guys are, at this point, now that they've kind of completed the foundation of the features that they want, and they're gaining some market share, they're all looking to add some form of search, because this is what the users want, and they want their solution to be as popular as other solutions. So they're all kind of adding search. So MongoDB has a built-in search feature. It's kind of similar to most relational databases. I don't know if you know like Oracle full text search, in that it's not super performant. It doesn't have tons of features. It doesn't work with tons of languages. They'll admit this in their documentation. It's early stuff. So if you need something really basic, you can use Mongo's new built-in full text search. Most people are sitting a real search engine like Solr next to it. And then you kind of have synchronization problems, but it's kind of pretty much what most people in the database world ended up doing too. You sit a real search engine next to it. You don't use the kind of built-in crappy search that eventually is going to get better, but we'll see. So that's kind of how the Mongo search. Next thing I want to talk about, Cassandra. Seems to be the next most popular NoSQL search engine. Their data model is column-based, like Bigtable, which is interesting because their distribution is similar to Dynamo. So basically what they did is they took how HBase stores data, which is really good for analytics, and they took how Dynamo distributes data and handles clustering, and they merged them into one idea, which is, I think, pretty cool. One of the big differences in how they do that compared to Dynamo for data versioning and consistency is that to make sure the same update wins on every node when you add a document to a node and that document has to be distributed to other nodes, is they use timestamps. So you pretty much have to use NTP and make sure all of your servers have roughly the same time. Otherwise, you have problems. And so you got to be careful. Like this is one of the things I really don't like about this. Dynamo actually uses something called vector clocks, which is basically a vector of counters that every time an update hits a node, the counter for that node increments. And you can kind of look and compare these vectors and kind of see which document should win on which node. Or you can see that there's a write-write conflict that you can't automatically resolve, and you can shove that back to the user, and he can tell you which document should have won. With timestamps, it's more just last document wins, and you're kind of at the mercy of your timestamp resolution on how fast you can do updates. If you're doing millisecond timestamps and you're updating faster the same document more than 1 millisecond, then that can cause problems. I've definitely read about people who have had that problem. And I don't like the idea of people having to run NTP, although even with SolrCloud, there's not as big a problem with time skewing, but if times do skew crazily, you do have problems. Almost all of these systems have, the time can't skew from each other that much, but some of them are more sensitive than others. Cassandra, I think, is pretty sensitive to that. So I guess a little more. So Cassandra, basically, it's a CA system like Dynamo. Sorry, not CA, AP system like Dynamo, in that basically every single node is a master, which is kind of cool. So basically, when you send a document to any node in Cassandra or in Dynamo, it doesn't have to talk to other nodes to accept that document. Every node can accept the document. And the way that it gets away with this is that, okay, so if you have partitions and that node can't immediately send that update to other nodes because maybe a couple of your switches went out and you have 2 independent clusters, basically both of them will keep accepting updates. And then later, either using the timestamps or the vector clocks, when you fix those switches or whatever, and the 2 clusters come back together, basically that's when you deal with the conflicts. Either by last update just happens to win, or you present it back to the client, and the client can tell you which update should win. And so this is what I mean by favoring write availability. You can always write to every node, because if there's any conflicts because someone else is updating the same thing on another node, then that's resolved later. In strongly consistent systems, you can't do this. So that's what's called eventual consistency, right? Eventually, when all of your nodes get back together, it's going to become consistent. Things will be fixed, either through like read repair or various other strategies. Whereas with a strongly consistent system, you can't. If your cluster is split in half, one half basically has to stop functioning. Because otherwise you're going to lose consistency. So that's the Cassandra model. For searching Cassandra, there's a variety of options. One of the very early ones was called Lucandra, and one that was built on top of that is called Solandra. These basically tried to, instead of storing the Lucene index on disk in the standard Lucene formats, it tried to basically have the data model live in Cassandra, so that you basically wrote the Lucene index onto the Cassandra storage. Like basically terms would be rows or columns, and so Lucandra basically distributed by term, Solandra distributed by document. There's a lot of negatives to these things. Field caches, if you distribute it by term, like doing field cache stuff was almost impossible. If you looked at a lot of the early code in this stuff, they would have like their own implementation of index reader, and some of the methods would like just return null or return -1. And they had to skip out on stuff to get all this to work. For the right like use case, I think some of this stuff worked all right, but in general, there were so many restrictions when you do this that these things never really caught on. DataStax actually has an enterprise search offering, which I don't know too much about because it's not open source. Like I think you have to buy the enterprise product to use it. They stopped. They moved beyond pretty much what everyone eventually does. They moved beyond trying to distribute the data layer of Lucene, and they actually write out Lucene indexes on each node. And so they'll use their architecture to distribute documents, but they'll still write standard Lucene indexes, which I think is a much better thing. You still have various limitations usually with these things. Like one of the ones I noticed when I was looking at their documentation is it said Solr fields must be strings, which, you know, for the right use cases may not matter, but not being able to use tree fields and numerics for me, and that's a killer. If I want search for my NoSQL search engine, I want something like Solr or any other Lucene-based thing to be able to use all of the Lucene features and to be as fast as Lucene and have all of the same features as Lucene. I really hate the idea of marrying Lucene to something and having to make these trade-offs. But that's basically how pretty much all of these NoSQL search systems work, lots of trade-offs. Next system in popularity is pretty much HBase, data model, column store, you know, really good for analytics, like I said, because you can load values for a lot of different documents or rows without doing any seeks. The distribution model for HBase is actually pretty cool. They get to rely on HDFS, which is a distributed file system. So basically, HDFS does the replication for HBase. You don't have to send a document to HBase, and then it has to figure out how to get it to the other servers. All that's handled by a lower layer, HDFS, which is based on Google's GFS distributed file system. So basically, HBase has like the single master concept, and the single master will divide all of the data up into what are called regions. And then you have what are called region servers. And so the master also says which of these region servers should search which regions, which is kind of like sharding the data in a way, although it all lives in one place on HDFS. And so what's kind of interesting about this is this is how they get strong consistency. They don't actually have replication for reads. Like a lot of times you might want to replicate so that you have more than one machine just because you get so many reads, you'd like to be able to split those reads across machines. So they've only got one machine serving each region. And if that machine goes down, HDFS will still be running. So what you can do is just start another region server and it will get assigned. Well, you don't even have to start one. Any of the other existing servers can get assigned those regions for whatever the server that went down, it's not serving that region anymore. Another server will just get assigned that region and start serving it. So you lose some availability because while that transition is happening, you can't do updates to that region for that moment. But you know, shortly thereafter, that'll be served again. So having a distributed file system kind of handle that stuff for you has some advantages, I think. And it allows it to have strong consistency, which is great for doing things like counters, which is much harder to do in something like Cassandra. Although people do kind of crazy stuff to make counters and things work in Cassandra. So HBase Search, there's a variety of HBase Search solutions. One was called HBase Scene, seems to be dead. It's been a few years since it's seen any commits. There's a HBase Jira issue that tries to add like Lucene or Solr for search, also seems to be dead. There's something called Solbase that PhotoBucket uses, which uses a similar idea as Lucandra and Solandra, which I think is kind of the wrong approach to scaling Lucene or Solr. And then there's something called Lily by ngData, which basically runs Solr separately, and it just handles, you know, if you do updates to HBase, it handles making sure that those updates get propagated over to Solr, which I think is probably a better solution than all of these other options. Another one that I want to talk about real quick is called Riak. It's a key value model that's based on Dynamo, so very similar to Dynamo. Has vector clocks to handle consistency. Has the option of also using timestamps. Generally, last write wins, although you do have the option of having clients resolve conflicts. So basically, if it detects a write-write conflict, it'll mark that, and when a client gets that back, it'll say, hey, there's a conflict here, tell me which one of these should win. Doesn't seem to have picked up a lot of steam or be super popular yet, but it's got a lot of options, and it's kind of a neat search engine. So it's actually got something called Riak Search built into it. It's a custom search engine that kind of simulates the Solr HTTP APIs, so it kind of looks like Solr, but it's not. It's their own kind of non-scalable whatever. They've got a next generation open source search solution coming called Yokozuna, which seems like a much better solution. So the Yokozuna author, he actually in a recent talk kind of enumerates why they're ditching their search solution. So their search solution is kind of like what MongoDB is doing, recreating something not based on Lucene, kind of their own thing, and they pretty much all end up with the same problems. For him, one of the things was that because they kind of simulated the Solr API, people expected it to behave like Solr, and when it didn't, they were confused. So Mongo doesn't have that problem. I don't think it tries to simulate the Solr API, but beyond that, lack of analyzers, languages, features. Lucene and Solr have a ton of analyzers to support a ton of different languages. They have a ton of different features. Someone who doesn't specialize in search is part of their main core mission for their company, trying to catch up to Lucene and Solr on these things. It's generally, I think, going to be a losing game, and I think Basho kind of realized this. Bad performance, resource usage for certain queries. I mean, it pretty much comes down to the same thing. When this isn't the primary thing you're working on, trying to make all these things that everyone has already made really fast in Lucene and Solr fast in your little custom search engine, not so easy. And basically, last thing you put, Basho is not in the business of search. I mean, I think that's what it really comes down to. If you're not in the business of search, trying to catch up with multiple companies who are contributing to Lucene and Solr, and an open source project that is in the business of search, that's trouble. And I mean, these days, when it comes to search engines, Lucene pretty much rules. If you don't have something based on Lucene, I think probably you're not going to last very long. It's just come so far, so fast. It's so good. It really doesn't have a lot of competition anymore, I don't think. Finally, real quick, let's talk about CouchDB. CouchDB, data format, JSON, conflicts. This is basically also an AP system, except things aren't really determined automatically. If there's ever a conflict, it's basically just recorded, and when a client pulls that back, it sees, hey, this is the right conflict I have for the updates. Tell me which of these updates should win. Yeah, like I said, CouchDB, it's got some popularity. A lot of people have heard about it, but it doesn't seem to be too high on the list, so I probably won't talk much about it. There's something called CouchDB Lucene that kind of integrates Lucene roughly with CouchDB. It doesn't seem to be that popular. It seems that most people, when they're using Couch and they want to do search, they just stick a search engine next to it. And then just to mention, because they're really popular, Redis and Memcached, they're a little bit different than these other solutions, and they're not really made for storing things on disk durability. It's more like caching systems. But there's still a lot of similar concepts to these other NoSQL solutions, and they still have search needs. There's something called Redis Search for searching Redis. So they're kind of interesting, but different than most of the other solutions. So basically, most of these guys, in one form or another, either the users or the companies behind the projects, they're trying to add search so that you can take your NoSQL search engine and search all of that data. And it generally seems to be pretty hard to do without a lot of compromise. Every one of those search solutions that I mentioned, it's not like using Lucene or Solr. You get some of the features, but a lot of the features either don't work or have major performance problems, or they're not using Lucene and Solr, and there's major feature and performance gaps. So everybody is like trying to add search, but just like when Oracle or whoever was trying to add database search, the solutions are not that great, and most people just end up running a search cluster next to their NoSQL cluster. And what kind of sucks about that is the consistency, handling, what happens when some documents fall out of your search cluster, but they're still in your NoSQL structure. I mean, what do you set up something that occasionally scans through it and sees what's missing and adds it back to the search thing? I mean, that's pretty much what I had to do at one point. The first search engine I made is I had a database and I stuck a search engine next to it. And after so many consistency problems, eventually I just started using the search engine as the database. I wasn't doing any joins or anything anyway. And so that seemed like the way to go. So that's pretty much why people are looking, I think, to integrate search closely, is because of this consistency problem. The problem is nothing has gotten that good yet, right? You don't hear about anything that has set the world on fire when it comes to a built-in search solution for NoSQL. You pretty much hear people using Lucene-based solutions, and that's it. Now, on the other hand, adding NoSQL to search. This seems like, in some ways, an easier problem to me. Search solutions like Solr are pretty much already document-based NoSQL engines. They don't have all the same features, but you know, even Solr, before it had clustering and it was just master-slave replication, that's eventual consistency. That's kind of a NoSQL system, right? Maybe not exactly the one you wanted, but it fits the bill. And search is fully integrated, and all of the features are performant and exist. So it's kind of already an interesting NoSQL option, although obviously lacking in a lot of features for the other NoSQL solutions. So nothing has set the world on fire yet when it comes to this either, but I think the interesting idea is that people trying to add search to NoSQL, I think, are going to continue to have a lot of trouble, right? We're going to keep innovating. They're going to keep trying to plug Lucene and Solr into their solution and making compromises, and we're going to keep innovating and adding features that they're not going to be able to keep up with. The compromises they make are going to compound, and they're just going to keep falling further behind, right? But when you think about a search engine as a NoSQL database, we've already got to accept data and distribute it across the cluster and do kind of all the same things that they have to do. Maybe we don't have all the features, but we have all the same problems. So when you make a distributed search engine, I think it's just the idea that that could be the search plus NoSQL solution seems to fit a lot more than a NoSQL solution integrating search and that becoming the NoSQL search solution. So basically, I guess my guess is that down the line, a search engine is going to be a very popular NoSQL solution. At the moment, I don't think that's the case. Obviously, Mongo is the #1 solution. Cassandra and HBase are there. Solr is, according to DB Engines, more widely used and popular than them, but it's not generally known as a NoSQL search engine. It's known as a search engine. But I think over time that's going to change. And it's not going to, I think, destroy these NoSQL options, right? Because of the different architectures, because you have the AP and the CP systems, and you have the column store data stuff for analytics versus the key value stuff, there's too many options depending on the use case for, say, something like Solr to displace them all. But I think that it could displace, or something like it could displace, say, the MongoDB architecture. Solr is very similar to the MongoDB architecture, right? It's master-slave, sharded. It's not similar to Cassandra. It's not really similar to HBase. It doesn't really shine in the same areas they do. But it's very, very similar to MongoDB. And so it seems like kind of a crazy statement with MongoDB making so much money and being so popular, but I predict its downfall eventually to a search engine. I don't predict the same with Cassandra or HBase. But OK, so Solr and SolrCloud and NoSQL. Solr is not the end-all, be-all NoSQL solution. If you came here expecting to hear that, I'm sorry, I won't say it. But we've started down that line, right? It kind of was a NoSQL database before, a document-based NoSQL database, if you kind of want to stretch the term. But before SolrCloud, it was definitely missing some things. And so some of the things that we've added to kind of make it a better NoSQL search engine already is something called real-time get. So before real-time get, if you added a document to Solr, you couldn't actually retrieve it until you did this kind of heavy reopen operation where an index searcher has to reopen and see the latest data. And so you could add a document and then query the database, and you won't see it right away. And so real-time get is the ability to say, it's not a search thing. It's here's the ID of the document I want. Give it to me. And so you don't actually have to go to an index searcher to see it. Basically, if it's been added, then you will find it. And basically, we use a transaction log to be able to do that. So when documents come in, they go to the transaction log first, and when you do real-time get, it looks in the transaction log for the document before, if it doesn't find it, then it can go to the searcher and pull it out. And so it's not a search time operation, but it basically lets you use Solr like you might use something like MongoDB. The other thing we added was update durability. In the past, because we didn't have that transaction log, if Solr went down and came back, you might lose data. Added a transaction log so that goes away. All these other NoSQL solutions work this way, so I mean, not having that is no good. Another thing we added, atomic compare and set. This is something that's really hard for something like an AP system to do because clusters can be isolated from each other. And so things like optimistic locking and atomic compare and set are very hard. These are things that HBase, something that's strongly consistent, can do fairly easily, or something like Mongo can do fairly easily. But these AP systems cannot. And so basically, atomic compare and set lets you say, you know, I've got a document, it's got the value 10 in it. I don't want to know that it has the value 10 in it, just whatever value it has, add 5, something like that. You can't do that with these AP systems, but it's kind of a nice NoSQL feature that things like HBase have. Versioning and optimistic locking we added. Like I said, another thing that's hard in AP systems, there are people who have kind of hacked in ways to do optimistic locking with Cassandra, but there's no real simplistic way to do it. Because SolrCloud is basically a CP system. And actually, one of the main reasons that was chosen is because of optimistic locking. When we first started thinking about how to do SolrCloud, I was talking to Yannick, and he pointed me to the Amazon Dynamo paper. And initially, we were looking at doing things kind of in a Dynamo way, an AP system way. In the end, Yannick is actually the one that pushed to switch to a CP system because he wanted optimistic locking. And you can't really do that when you need to be able to accept writes and all your nodes can't talk to each other. Optimistic locking, you know, pretty much requires that you know what the latest value for a document is, and if documents are distributed and can be eventually consistent, that's kind of trouble. Another thing to mention, because this is kind of, schemaless is kind of heavily associated with NoSQL. When you talk about NoSQL, you talk about schemaless. When you talk about Solr, you're generally not thinking schemaless. So it's definitely an issue to talk about. So what does it mean to be schemaless in a NoSQL database? Basically what it means is most of these things are either key value or key document stores. And so it means, okay, that key value can be anything. The value, in a key value store, the value can be any binary blob or whatever. So right, there's obviously no schema. They don't care if it's an integer, a string, a byte array, whatever. Same with documents. Documents can be JSON. The JSON can have any structure or any data in it. There's no real schema. So this is kind of a big thing. People seem to like this. Oh, great. I don't have to do any upfront work. I can just throw data into the system and then deal with it. But right, you're not really actually dropping the schema in this case. You're just kind of moving it. Your application code still needs to understand how to read these things and still needs to basically understand the schema, right? If you've got a bunch of integers rather than a bunch of names, the application code needs to know that they're integers and I can add them, or they're names and I can deal with them as strings. You can't add an integer to mark. So basically, you still have a schema, but it's in the application code, and that has upsides and downsides. It has, you know, basically upsides because when you're adding all your data to your system, you don't have to worry about it. Not until you're writing your app that accesses the system do you have to worry about it. Some of the downsides are, okay, if the schema lives in the application code, when multiple people are writing applications that access the same NoSQL database, they've all kind of got to know the schema and put it all into the different applications that they write, which is kind of a downside. Other downside is the database itself can't optimize based on types, right? When Solr, if you use an integer, these days we don't store that as just like we would a normal string anymore. We optimize it because we know it's an integer and we can store it more efficiently in a way that we can do operations on it more efficiently, and so you kind of lose that ability. Basically you still have a schema, you've moved it, I guess is my main point. The other thing is like, so some other solutions are saying that schemaless, that they have schemaless when what they're really doing is guessing the schema. You know, if you're using a Lucene-based solution, Lucene has some sort of implicit schema. It just does. So you either need to define it or you need to write some code that guesses it. At the moment with Solr, you pretty much have to define it, although I know that like Steve Rowe is working hard towards making it so that we have the option of guessing it, which, you know, when you're prototyping might be nice. So, I mean, that's kind of one way that Solr is probably going to be a little bit different when it comes to NoSQL, is that when you're dealing with a search engine, you really can't throw out the schema as easily as you can with just a basic storage engine. Because we really, to be efficient, you really want to know the types. So either guess them or have the user tell you what they are. Yeah, so finally, like I said, Solr and SolrCloud is most similar to the MongoDB architecture. And that's why I think Mongo is the vulnerable NoSQL solution to search NoSQL solutions. It may take a while. They may figure out how to avoid that from happening. They've got a lot of money. But honestly, I think as they try to add search and these systems try to add more Mongo-like features, I think the search engines have the advantage. So that's I guess, my main thought of this talk. So like I said too, SolrCloud, it's a CP system. It's not actually strongly consistent the way that Mongo and HBase are at the moment, although I think the architecture does allow that. But the way that we've implemented it at the moment, it's eventually consistent, just with a very small window. Like, so some eventually consistent systems like Dynamo or Cassandra, the eventualness window can be pretty wide because clusters can get partitions and split out from each other, and you don't know how long until they come back together. With SolrCloud, if partitions separate your cluster, then the ones that don't have basically the majority of Zookeeper nodes are going to die off. So you still only have one cluster. So the reason that we're eventually consistent is because when you write updates to the master starts sending them to replicas, and a third party who's doing searching might hit one node and see a document and really quickly search again and hit another node that doesn't have that document yet. So it's a very small window because the master is sending those documents kind of concurrently at the same time to each node. But if you're searching really, really fast, you do have to know that it's very mildly eventually consistent. The way we did the architecture, though, there's definitely options and knobs that we're going to add to give you the ability to do something that's strongly consistent. 2:30. Anyone know when this talk ends? 2:35. All right, yeah. So I'm going to stop then, and if anyone has questions, then. Moderator? Hand the mic to people.
Questions?
Can I use Solr as a NoSQL database instead of using MySQL? Because I'm consider using Solr like a cache. I need initial data, then I should input the data and search for them.
Right.
So if I drop my database, my SQL database, can I use it to, for example, reindex the whole Solr if I change schema?
I don't fully understand. If you drop, can you stop using MySQL and just use Solr?
If I change something in my schema, I should re-input everything.
Yeah, I mean, if you store everything as a stored field, then it becomes pretty easy to reindex everything. If you don't, then, I mean, you got to have access to the original data.
So if I store everything in the stored fields, can I reindex it without re-importing?
Yeah, I mean, I think you have to write the code to do it now. I don't think there's anything automatically that will do it for you, but it's fairly simple code.
So I should just fetch all IDs and then cycling through them.
Page through the IDs and do it some at a time. I've definitely had systems that do that in the past. I think, it's probably a feature that we're going to build in before long. Just haven't gotten to it. But you can write some fairly simple code to do it, I think. I would just page through, right?
It's on the roadmap, but you have to do it yourself right now.
Okay, thank you.
I've got a similar question about using Solr as our only NoSQL database and not having to use Mongo or anything. And it has to do with we index documents and I want to turn right around and query them. So I want to use their near real time. If I use something like SolrJ and I'm going and hitting Zookeeper, I'm using SolrCloud, am I guaranteed that what I just wrote, as long as the soft commits occurred, that I'm going to get the...
As long as the soft commits occurred, but you either have to explicitly send that soft commit yourself, or
Right.
if you're doing auto soft commit, wait long enough for it
Right,
to
wait a
trigger
second or
behave.
whatever. But I don't have to worry about going to a node to get that, to actually run the search and not have those documents available where it hasn't spread to all the replicas yet.
You do have to worry about that a little at the moment, don't you?
Right now, we write to all the replicas, right? So
Right.
once
Oh,
it-
yeah,
once
yeah.
it
Okay. So if you're the one that wrote the document and it
Right.
returns, then yeah, you're guaranteed that it's on all the nodes.
Oh,
It's
okay.
only a third party that might see things.
Gotcha. So how long would I expect? Well, I guess it depends on the network. I know she kind of skipped that slide about when it's all consistent.
Oh, only 5 minutes left.
Yeah, okay.
Thank you.
Hi. Actually, I have two questions because I was looking forward to your talk. The first one, I know that Solr shines when you have concerning the caching, and when you want to use Solr as a NoSQL solution, definitely I have to take care how I'm configuring document cache. It should be probably much bigger. And the question is, what kind of implications has on a garbage collection? And I know that in HBase they are taking really care of using local allocations buffers, for example, that I'm allocating the memory in the same chunks when I'm using garbage collection, that I can efficiently reuse the free memory. That was the first question. That means, how I am going to configure the garbage collection and what is happening with the document cache? That was the question.
Yeah, I mean, honestly, we're just having this conversation earlier where some people were telling me they don't think the document cache is so useful anymore. So yeah, I mean, those caches definitely have impacts on GC, and especially if you're using near real time and you're invalidating the searcher that keys those caches all the time, then you're having extra GC problems. So I don't know, Yannick, you're still a proponent of the document cache? Maybe just don't use it.
Yeah, but here I'm talking about, for example, what I know in HBase, because we are using HBase, that cache that you are using for fast reads is something like 40% of the heap. It means I'm guessing if you are using Solr as a key value, as a NoSQL, you have to be able to cache a lot of what you need in order to...
I think for most of that stuff, you want to count on the file system cache to have it cached and not the heap.
Okay, but eventually it's going to be not real-time get, but that document is going to finish in index and in a store files, and you're saying we should rely on a file system cache that if that document is often needed. Okay, and the second question, I was hoping that you are going to touch that about sharding, and the question is, I know that SolrCloud uses Zookeeper, and if I am in my shard, I'm writing the custom component, and I want to have a small amount of information that I'm going to exchange between shards because I want to use that information in query routing. Is that a good idea to simply say to my component, okay, you have a Zookeeper, and you are going to write that information in Zookeeper, and another shard is using that information, actively listening on the information in Zookeeper and using that information for doing better query routing?
I guess it depends how often you're writing it. You don't probably want to be, like, on every request writing something to Zookeeper and then having other things read it.
Let's say that always when I'm committing, maybe.
Yeah.
That's maybe.
Yeah, that could make sense, perhaps. And then you could set up watchers and stuff so that the other shards know about it. I mean, I would just say don't write and read from Zookeeper per request. But if you did it something more like per commit, then that could make sense. And yeah, I wanted to get more into sharding and other stuff, but honestly, I thought I was going to blow through a lot of those slides a lot quicker, and so I didn't get to it.
Okay, thank you.